Hello students, welcome to my online class of Partial Differential Equations Module 3. Today's topic is Solution of Partial Differential Equations. Under this topic, we shall consider the solution of a homogeneous partial differential equation involving derivative with respect to one independent variable only. Now, a homogeneous partial differential equation is a partial differential equation in which each term contains either the dependent variable or its partial derivative. The homogeneous partial differential equations which we shall consider involve only derivatives with respect to one independent variable. So let us see how we solve such an equation. Since the partial derivatives involved in the equation is with respect to one independent variable only, so we can consider the equation as an ordinary differential equation and find the complementary function. In the complementary function, constants will be involved, but since we are considering a partial differential equations, the constants in the equation cannot be purely constants. They will be functions of the variable treated as constant. That is the variable which does not appear in the differential equation. With the help of the conditions given in the problem, we shall find the values of these arbitrary functions and get the required solution. So let us take up a numerical example now. The first example which we have taken is solve dou square z by dou x square plus z equal to 0, given that when x is equal to 0, z is equal to e to power y and dou z by dou x is equal to 1. These are the two conditions given. So since this partial differential equation contains partial derivative with respect to one independent variable only, that is x, so treating this equation as an ordinary differential equation, we are able to write down the auxiliary equation as m square plus 1 equal to 0. We can find the roots of this auxiliary equation as m equal to plus or minus I. Since they are complex roots, so we can write down the complementary function as z equal to a cos x plus b sin x. Now this is the complementary function treating the given equation as an ordinary differential equation. But since z is a dependent variable function of x and y, x and y, x is already in the equation, and in the conditions, as you can see, the variable y has come, so z is a function of x and y both. So instead of a and b, we shall replace a and b by functions of y. So z is equal to f of y cos x plus g of y sin x. So a and b here are not treated as constants, but instead they are functions of the variable treated as constant, or the variable which has not appeared in the equation as such, but in the conditions they have appeared. So y is an independent variable here. So with the help of the conditions given, we shall find the values of the arbitrary functions f of y and g of y. Now let us consider the first condition given here. When x is equal to 0, z is equal to e to the power y. So in equation 2, the complementary function which we have written down, in equation 2, we'll apply this condition x equal to 0 and z equal to e to the power y. So when x is equal to 0, we know that cos 0 is 1 and sin 0 is 0. So let us apply here. So in place of z, we write down e to the power y, f of y cos 0 plus g of y sin 0. Now sin 0 is 0, cos 0 is 1. So this term cancels and this term becomes just f of y. So we write down equal to f of y. So the value of f of y is e to the power y. Now substituting f of y value in equation 1, equation 2, we get z equal to e to the power y cos x plus g of y sin x. We number this as 5. We have yet to find the value of g of y. So let us apply the second condition given here. When x is equal to 0, dou z by dou x is equal to 1. Since a partial derivative is involved here, so the equation 5 has to be differentiated with respect to x, and then we can apply this condition. So differentiating 5 partially with respect to x, we get dou z by dou x equal to e to the power y. This is a constant with respect to x. So e to the power y, derivative of cos x is minus sin x, plus g of y is again a constant with respect to x. So as it is, and derivative of sin x is cos x. So in this equation now, we shall apply the condition when x is equal to 0, dou z by dou x is equal to 1. So in place of dou z by dou x, we write on 1 equal to e to the power y into minus sin 0 plus g of y cos 0. Now cos 0 is 1, so this is g of y into 1, g of y. Sin 0 is 0, so this term becomes 0. So we get g of y equal to 1. Now substituting g of y in 5, we get z equal to e to the power y cos x plus sin x. Both the arbitrary functions are eliminated. We have got the required solution. Now let us take the second problem. The second problem is solve dou square z by dou x square equal to a square z, given that when x is equal to 0, dou z by dou x is a sin y and dou z by dou y equal to 0. Here again you can see this is a homogeneous partial differential equation, because each term either contains the independent variable z or it contains the partial derivative, and the partial derivative here is with respect to one independent variable x only. So treating this equation as an ordinary differential equation as earlier, we can write on the auxiliary equation as m square equal to a square. So m is equal to plus or minus a. The roots of this auxiliary equation are a and minus a. So the complementary function can be written as z equal to a e to the power ax plus b e to the power minus ax. All this we have already studied in module 1, differential equations. So this should not be something new. Again, since z is a function of both x and y, so a and b cannot be pure constants, but they are functions of the variable held fixed, that is function of y. So we write down a as f of y and b as g of y to get the complementary function z equal to f of y into e to the power ax plus g of y e to the power minus ax. Now let us apply the conditions so that we can write down the values of the arbitrary functions. So when the first condition is when x is equal to 0, dou z by dou x is equal to a sin y. Since a partial derivative is involved, we cannot directly apply in equation 1. So we have to differentiate one partially with respect to x and then apply this condition. So differentiating one partially with respect to x, we get dou z by dou x equal to f of y into f of y is a constant with respect to x. So f of y as it is into derivative of e to the power ax. Derivative of e to the power ax is a e to the power ax plus g of y is a constant. Derivative of e to the power minus ax is e to the power minus ax into minus a, or dou z by dou x is equal to a f of y e to the power ax minus g of y e to the power minus ax. What we have done is we have taken a as a common factor. Now applying condition 2 in 3, we get a sine y equal to a times f of y minus g of y. Now we know that when x is equal to 0, e to the power a into 0, that is e to the power 0 is 1, and e to the power minus a into 0, e to the power again 0 is 1. So this is 1, this is 1, so f of y minus g of y. So we get f of y minus g of y equal to sine y, and we number this as equation 4. These are still unknown functions. Now applying the second condition, that is when x is equal to 0, dou z by dou y is equal to 0. Again here partial derivative is involved, so directly this condition cannot be applied to 4. We have to differentiate 4 partially with respect to y. So dou z by dou y is equal to f dash of y. Now we are differentiating with respect to y, so derivative of f of y with respect to y is f dash y, and derivative of g of y with respect to y is g dash of y. So differentiating 1 with respect to y, we get dou z by dou y equal to f dash of y e to the power ax plus g dash of y e to the power minus ax. Applying now this condition 5 to 6, in place of dou z by dou y we write down 0, and x is put as 0, so this becomes 1 and this becomes 1, this becomes 0. So 0 is equal to f dash of y plus g dash of y. Here f and g are purely functions of y only, so these are ordinary derivatives with respect to y. Now since we have got f dash and g dash, we require f and g, so we integrate this with respect to y to get f of y plus g of y equal to a constant of integration c, which is a pure constant. Now adding 4 and 7, we get, you see that f of g of y here is with minus sign and g of y here is with plus sign, so when you add they get cancelled, so you get 2 f of y equal to c plus sine y. So f of y becomes equal to c plus sine y by 2. Subtracting now 4 from 7, we get 4 from 7, we get g of y equal to c minus sine y by 2. F of y gets eliminated. So substituting in 1 the equation which contains f of y and g of y in the complementary function, z is equal to c plus f of y by c plus sine y by 2 into e to the power ax plus c minus sine y by 2 e to the power minus ax. Now expanding and then taking c common, on the right hand side, c times e to the power ax plus e to the power minus ax by 2 plus, now sine y is taken common, e to the power ax minus e to the power minus ax by 2. We know that e to the power ax plus e to the power minus ax by 2 is nothing but cos hyperbolic ax, and e to the power ax minus e to the power minus ax by 2 is nothing but sin hyperbolic ax. So our z becomes c cos ax plus sin y sin hyperbolic ax, which is the required solution.